So now I am going to discuss the solutions for the questions in the assignment in fiction, starting from 61 onwards. Come on, look at the question number 61. So when the blocks are at rest, we can consider the two blocks A and C together as one system of total mass equal to MA plus MC. Here T the tensile force exerted on the block A by the string, which acts along the string and away from the block A. So the force of static friction on the block A by the surface of the table acts towards left side. If you consider the blocks A and C together as one system, then you can draw the free body diagram for system of the blocks A and C. In this way, the total weight of system of the two blocks A and C equal MA plus MC into G, which acts vertically downwards. The normal reaction force on the block A by the surface of the table acts vertically upwards, perpendicular surface of the table and direct away from surface of the table. So the tensile force exerted on the block A by the string acts towards right. So the force of static friction exerted on the block A by the surface of the table acts towards left side. So when we consider the two blocks A and C together as one system, then the force on A by C or the force on C by A, they can be treated as internal forces. So the internal forces between the blocks A and C, I mean the contact forces between the blocks A and C, need not be shown in the free body diagram for the system when we consider the two blocks A and C together as one system. And the force exerted, contact force on A by C is an internal force. The same way the contact force on C by A is also an internal force. When the system is in equilibrium, the net force on the block system must be 0. So if net force in the vertical direction, if it is equated to 0, you get measure of normal reaction. On the system of the two blocks A and C by the surface of table MA plus MC into G, measure the tensional force exerted on the block A by the string should balance the static friction force. Coming to the block B here, the weight mg of the block B acts vertically downwards. There are two forces acting on the block B. The weight of the block B acts vertically downwards, so tension force on the block B by the string acts upwards. So net force on the block B is equal must be 0. So net force of block B can be written as MB into G minus T. That is 0 when the block B is in equilibrium. So measure of tension force of the block B is equal to MB into G. So from first and second equations, you can substitute the value of the tension T from first and second equations. So measure of static friction on the block A by the surface of the table, same as the measure of the weight of the block B when the system is in equilibrium. So, but measure of static friction cannot exceed the limiting value nu into n. So you can substitute MB into G on the left side. Magnitude of normal reaction on the block A by the surface of the table can be written as MA plus MC into G on the right side. So there must be nu here. You can cancel G both sides here. Therefore, you can write nu into mass of A plus mass of C. This should be greater than or equal to mass of B. So you are asked to find the minimum mass of C. Therefore, minimum mass of C required is equal to mass of B divided by nu minus mass of A. Come on, copy down the solution of the problem. You can substitute all the given values and simplify it to yourself. So you get the answer as 15 kg. Come on, copy down the solution of the problem. In case you need more time to copy the solution of the problem, you can take a pause and take more time. So for question number 61, second option is the answer. See the question number 62. Body of mass kept limb is kept on a rough horizontal surface. A person is trying to pull the body by applying a horizontal force, but the body is not moving. The force exerted by surface on the body is kept left. So here, kept left represent the magnitude of the contact force exerted on the body by the surface. I can say kept left is the magnitude of the total reaction force exerted on the body by the surface. So if FA is the horizontal force applied by an external agent towards right, then the force of static friction on the body by the surface of the floor act towards left side. So in the vertical direction, its weight mg acts vertically downwards. This part of the discussion actually I have done in the past when I discussed about the angle of friction. So the normal reaction force on the block by surface acts perpendicular to surface and direct away from surface. So in this previous diagram, N is the magnitude of normal reaction force on the body by the surface, and Fs represents magnitude of the static friction force exerted on the body by the surface in contact. So magnitude of the total reaction force or contact force on the body by the surface is the resultant of N and Fs. So that is equal to under root of N square plus Fs square. So maximum value of this force is equal to under root of the magnitude of the contact force. That means if you complete the rectangle with N and Fs by the adjacent sides, the resultant of N and Fs acts along the diagonal of this rectangle. This we call the total reaction. This total reaction, magnitude of this total reaction denoted by kept left in the given question. So Fs maximum value for the static friction equal to nu F into N. So that is N into root of 1 plus nu f square. As the block has no motion in the vertical direction, the weight mg of the block is balanced by normal reaction force. So maximum value of the force, maximum value of the normal reaction force is equal to, maximum of normal reaction can write mg, maximum value of the force F can be written as mg into root of 1 plus nu f square. And minimum magnitude of force is equal to F is minimum when Fs is minimum. When the horizontal force applied on the block is 0, then block is at rest, magnitude of static friction is also 0. Then F will be minimum. So F minimum value of F equal to root of n square plus 0 square or equal to n, which is equal to mg. That means F lies, the value of F in general lies between mg and minimum and maximum values. So mg is less than or equal to F, less than or equal to mg into root of 1 plus nu f square. So those who want to copy the working, they can take a pause and copy the working. This question was given one of the previous entrance examinations, as mentioned within brackets. So for question number 62, third option is the answer. Then see the question number 63. You can observe that a horizontal force of magnitude P is applied on the block of mass M towards right, which is resting on a horizontal plane, and a pushing force of magnitude Q is applied at an angle theta with the vertical, as shown in the figure. So you have to find the coefficient of friction between the block and surface for the block to be in equilibrium. So the pushing force is applied at an angle theta with the vertical. That means the direction of the pushing force is like this. The line of axis of the pushing force is produced backwards, produced in this way. This can also be taken as theta. So graphically, a given vector can be represented at different places in the diagram without changing its magnitude and direction. So you can draw a free body diagram for the block separately. So the weight mg of the block acts vertically downwards. And capital P represents the magnitude of the horizontal force applied on the block. And capital Q represents the magnitude of the pushing force applied on the block, which is directed at some angle theta with the vertical. So I'm trying to represent all the vectors graphically drawn from same point, such that the tails of the vectors are coinciding. The normal reaction force on the block by the horizontal plane acts perpendicular to surface of plane and directed away from surface of plane. This horizontal force P tends to move the block towards right relative to the plane. Therefore, force of friction between the block, the force of friction exerted on the block by the horizontal plane acts towards left side. If the block is at rest, then this frictional force will be the static friction. Can resolve Q into rectangular components along the horizontal and vertical directions. So the vertical component of the force Q, which makes angle theta the direction of the force, will have magnitude Q cos theta. The horizontal component of the force Q. The horizontal component of the force Q will have magnitude Q sin theta. You can choose the horizontal direction of the x-axis and vertical upward direction of the y-axis. So the y component is the resultant force. We denote it by F subscript y. That you can write N minus mg minus Q cos theta. Because the block is in equilibrium, this must be 0. So magnitude of normal reaction of the block by the surface of the horizontal plane is equal to mg plus Q cos theta. So the block will be in equilibrium when the static friction does not reach the limiting value. I mean, when the horizontal force which tends to move the block towards right along positive x-axis does not exceed the limiting friction. So the net horizontal force which acts along positive x-axis, which tends to move the block, has magnitude P plus Q sin theta. So block will be at rest. Does not move. The magnitude of the horizontal force which tends to move the block towards right does not exceed the limiting friction. That means this is less than or equal to nu s into n. You can substitute the value of n on the right side, or P plus Q sin theta has to be less than or equal to nu s into, you can substitute n equal to mg plus Q cos theta. Or you can say nu s into mg plus Q cos theta has to be greater than or equal to P plus Q sin theta. That means the minimum value of the coefficient of static friction required is P plus Q sin theta by mg plus Q cos theta. Can copy down the solution of the problem. So this will be the first option is the answer. So next I am going to discuss the question number 64. It's relatively easier problem. See the question number 64. Let us draw the tree diagram for the block. Block is placed on a rough horizontal surface. F is the magnitude of the horizontal force applied on the block, which has magnitude equal to 100 newtons. The weight mg of the block acts vertically downwards. The normal reaction force acts perpendicular to surface and contact directed away from surface. So when the block is in motion, the frictional force on the block can be called as kinetic friction. It acts opposite direction of motion. You can choose the horizontal direction, the direction of the motion of the x-axis, and vertical upward direction of the positive axis. So the y component resultant force of the block is n minus mg, that is 0. So magnitude of kinetic friction, you can write nu k into n. Here n equal to mg. Nu is given to be 0.5 here. M is 10 kg. If you take g as 10 meter per second square, so you get 50 newtons. So horizontal force applied on the block is clearly less than the frictional force on the block. So resultant force of the block in the horizontal direction has magnitude F minus Fk. From Newton's second law, that can be written as equal to mass into acceleration. You can substitute magnitude of the horizontal force equal to 100 newtons, magnitude of kinetic friction equal to 50 newtons. Mass of the block is 10 kg. You have to find the magnitude of the acceleration of the block. Come on, complete the calculation, simplification yourself. So for question number 64, third option is answer. See the question number 65. This problem comes under one of the special cases which I have discussed earlier. So when the, let us suppose the truck is moving towards right, let A denote the magnitude of the acceleration of the truck. The forces, let us consider the force acting on the block. Similar discussion I have done in the past in one of the special cases, and also similar problem I have discussed in the past. So the weight mg of the block acts vertically downwards. See the gravitational force of the block by the earth. The normal reaction force on the block by the surface of the truck acts vertically upwards, perpendicular surface of truck and direct away from surface of truck. So here the truck is moving towards right with respect to stationary observer on the ground. So in case if there is a slipping between the block and the truck, then the truck moves towards right relative to the block. So the truck tends to move towards right relative to the block. Therefore, force of friction on truck by the block will act towards left side. From Newton's third law, there will be to every action there will be always equal and opposite reaction. The frictional force on truck by the block acts towards left side. Then the force of friction on block by the truck acts towards right side. So if the block does not slip on the truck, this frictional force will be the static friction. Let us consider the condition here. So we choose the horizontal direction, that is the direction of the motion of the block as x-axis. I mean with respect to stationary observer on the ground, the direction of the motion of the block is same as the direction of the motion of the truck, that is towards right side. So if the block does not slip on the truck, then this frictional force can be called as static friction. Then resultant force of block in the vertical direction is 0. That is Fy equal n minus mg, that can be 0 or magnitude of normal reaction of the block by the surface of truck. You can take it as mg. And resultant force of block in the horizontal direction is equal to Fs. So magnitude of the resultant force of block with respect to laboratory frame of reference. I mean with respect to stationary observer on the ground. Is the force of static friction exerted on the block by surface of truck which act towards right in the direction of the motion of the block. From Newton's second law, that is equal to mass into acceleration. So, but static friction cannot exceed the limiting value nu s into n. So, you can write here Fs equal to me on the left side, n equal to mg on the right side. So, you can say that conclusion of the discussion is that so block does not slip on the surface of the truck if the acceleration of the truck is less than or equal to nu s into g. So, in the given example, nu s is given to 0.6, g is 9.8 meter per second square. So, therefore, we can say that the block does not slip on the surface of the truck if the acceleration of the truck is less than or equal to 5.88 meter per second square. So, in the given problem, it is given that acceleration of the truck is 5 meter per second square, which is definitely less than nu s into g. Therefore, block will be therefore block does not slip. I mean, block will be at rest with respect to truck, but with respect to stationary observer on the ground, the block moves horizontal along with the truck with the same acceleration as the truck. Therefore, block does not slip on the surface of the truck. Therefore, from this equation, magnitude of static friction on the block by the surface of truck is equal to m into a. The mass of the block is 1 kg. Magnitude of the acceleration is 5 meter per second square. Therefore, the magnitude of the force of friction unblocked by the surface of the truck has magnitude of 5 newtons. Okay, if you want to copy the solution, you can copy down the solution. For question number 65, first option is the answer. See the question number 66 here. This problem also comes under one of the special cases which I have discussed already in the past. As discussed already in the past, please you refer to the discussion I have already done in the past for this special case. So if a block of mass m1 rests on another block of mass m2 which rests on a smooth horizontal floor, then if a horizontal force applied on the lower block, the two blocks move together with the same acceleration. Already discussed here this special case in the past. So the two blocks move together with a common acceleration The horizontal force applied on the lower block less than or equal to nu into MA plus MB into G. Here mass of A is 10 kg, mass of B is 15 kg, nu is 0.2. So sum of the mass of A and B is 10 plus 5 kg. So that comes out 15 kg. Let us take G as 10 meter per second square. That means the two blocks move together with the same acceleration if F is less than or equal to 30 Newton. But here the magnitude of the horizontal force applied on the lower block is 50 Newtons. I'm sorry, 40 Newtons, which is more than 30 Newtons. That means the horizontal force applied on the lower block is more than U into MA plus MB into G. Therefore, there will be slipping between the two blocks. They do not move together with the same acceleration. When they do not move together with the same acceleration, the type of friction that exists between the two blocks, when there is relative motion between the two blocks, is called kinetic friction. So here, the velocity of the block A relative to B is directed towards right side. I mean the horizontal force applied in the lower block A tends to move the lower block A towards right relative to the upper block B. Therefore, force of friction on A by B acts to the left side. That is the kinetic friction. So the force of kinetic friction on B by A acts towards right side. You can draw a separate free body diagram for each block. So in the horizontal direction, two forces act on the block A in opposite directions. F is the horizontal force applied towards right side, and Fk is the force of kinetic friction towards left side. Let us first estimate the magnitude of kinetic friction here. So magnitude of kinetic friction between the two blocks is equal to product of coefficient of kinetic friction into magnitude of normal reaction between the two blocks. So magnitude of the normal reaction force on the block B by the block A can be taken as equal to weight of the block B, because the block B has no motion in the vertical direction when the two blocks are in contact. So this nu is 0.2 here. Mass of the block B is 5 kg. Let us take G as 10 meter per second square. So magnitude of kinetic friction will be 10 newtons. So magnitude of the resultant force on the block A in the horizontal direction is equal to F minus Fk. From Newton's second law, this can be the product of mass of block A and magnitude of acceleration of A. Here F equal to 40 newtons, magnitude of kinetic friction is 10 newtons, and mass of block A is 10 kg. Come on, you try to simplify this yourself. I solved this problem a bit faster because I have already done similar problem in the past, and just a repetition of this model for your practice. So you get magnitude of acceleration of A as 3 meter per second square. If you want to copy down solution, you can copy down. So for question number 66, first option is the answer. See the question number 67. A block of mass 4 kg placed on rough horizontal plane. A time dependent horizontal force F equal to kT acts on the block. K is 2 Newton per second. Of course, understood that small t time in seconds. The frictional force between the block and the plane at t equal to 2 seconds and t equal to 5 seconds will be. So let us consider the free body diagram for the block. So the block is here resting on a horizontal plane. The weight mg of the block acts vertically downwards. The normal reaction force on the block by the surface of the table, by the surface of the horizontal plane, acts upwards. Let capital F denote the magnitude of the horizontal force applied on the block. Let small f denote the magnitude of friction on the block by the horizontal plane which acts to the left side. We choose the horizontal direction, that is the direction of the force applied at the x-axis, in vertically upward direction as y-axis. So y component of resultant force of block is n minus mg, but the block has no motion in the vertical direction, this is 0, so magnitude of normal reaction is same as the magnitude of weight mg. So magnitude of the limiting friction is equal to nu into n, that is nu into mg. Nu is given to 0.2 here, mass of block is 4 kg, let us take g as 10 meter per second square. That comes out to be 8 newtons. So at t equal to 2 seconds, the magnitude of the force applied on the block is k into t. K is 2 newton per second and t is 2 seconds. That is 4 newton. That means which is less than 8 newtons. That means at t equal to 2 seconds, the magnitude of the horizontal force applied on the block is less than the limiting friction. Therefore, block will be at rest at t equal to 2 seconds. When the block is at rest, resultant force of the block in the x direction must be 0. So resultant force of the block in the x direction is equal to capital F minus magnitude of static friction. That can be correct. So magnitude of static friction must be same as the magnitude of horizontal force applied, which is equal to 4 newton. So that is the answer for the first part of the question. So block begins to move when the magnitude of the horizontal force reaches the limiting friction. So block starts moving when the magnitude of the horizontal force just exceeds the limiting friction by infinitesimal small amount. That means when k into t becomes equal to limiting friction is 8 newtons. K is 2 newton per second into t is 8 newtons. That means the block starts moving at t equal to 4 seconds. Strictly speaking, the block starts moving after this particular instant t equal to 4 seconds. When the magnitude of horizontal force exceeds 8 newtons. That means at t equal to 5 seconds, the block will be in motion. And magnitude of the friction force will be the kinetic friction nu k into n. That is nu k into mg. You are not specifically separately given the values of nu s and nu k, so you can take nu k to be nearly same as the given coefficient of friction, which is equal to 0.2. The mass of block is 4 kg, g is 10 meter per second square. So magnitude of friction can be taken as 8 newtons. So if you want to copy down the solution of the problem, you can take a pause and copy down the solution of the problem. So for question number 67, which I have just now discussed, the second option will be the answer. So look at the question number 68. So ladder weighing 250 Newton is placed against a smooth vertical wall having coefficient of friction between it and the floor as 0.3. And what is the maximum force of friction available at the point of contact between the ladder and the floor? So the wall is smooth, there is no friction force between the ladder and the vertical wall. So this is the wall here. So there will be one normal reaction force by the floor on the ladder. This is the ladder which is at slant, making some angle theta with the horizontal. The weight mg of the ladder acts vertically downwards, or let us denote the weight of the ladder by W. Of course, there will be another normal reaction by the wall, because the wall is smooth, there is no friction between the wall and the ladder. So therefore the contact force between the wall and the ladder will be normal to surface of wall. So N dash is the normal force exerted on the ladder by the wall. So this N dash has to be balanced by the force. If the ladder does not slip, then the friction force on the ladder by the floor can be called as static friction. So because N dash is directed towards left side, to balance this force N dash, static friction on the ladder by the floor act towards right. So if we choose the horizontal direction to the right side of x-axis, so vertically upward direction of the y-axis. So for equilibrium, resultant force 0. So x component resultant force can have Fs minus N dash, that must be 0. So magnitude of static friction on the ladder by the floor must be same as the magnitude of the normal force by the wall on the ladder. In the vertical direction, resultant force is N minus W. W is the weight of the ladder here, magnitude of weight of the ladder. That must be also 0 because the ladder has to be in equilibrium. That is equal to N equal to W. So the weight W is equal to 250 newtons here. So magnitude of the normal reaction on the ladder by the floor is 250 newtons. So maximum value of the force of static friction on the ladder by the floor equal to nu of c into N. That is equal to 0.3 into 250 newtons. That will be 75 newtons. That's the answer. So for question number 68, first option is the answer. So let us consider the forces acting on each block. The weight for the mass M1, its weight M1G acts vertically downwards, which will be balanced by the normal reaction force by surface of the table. Here N is the magnitude of normal reaction on M1 by the surface of the table. The tension force exerted on M1 by the string acts towards right, along the string and away from the mass M1. So the tension force exerted on the string by the mass M1 tends to move the mass M1 towards right relative to M2. The force of friction on M1 by surface of the table act towards left side. Coming to the mass M2, its weight M2G acts vertically downwards. So the tension force by the string on M2 acts along the string and away from the mass M2. Both the masses are acted by tension force of same magnitude. If the mass of string is negligible compared to the mass of the two blocks, so magnitude of tension will be same at both ends of string. The system will have, so blocks begin to move only when the magnitude of the weight M2G of second block, which tends to pull the mass M2 downwards, is more than the limiting friction on M1. Magnitude of limiting friction on M1 equal mu into normal reaction on M1. Magnitude of normal reaction M1 equal to u. So the two masses begin to move. If M2 by M1 is more than u, here M2 by M1 is 1, that is more than u because nu is 0.5. Therefore the blocks begin to move. Both the masses move with same magnitude of acceleration. So magnitude of resultant force on M1 in the horizontal direction is equal to T minus magnitude of friction force. That will be the kinetic friction. From Newton's second law, that you can write mass of the M1 and magnitude of its acceleration. So resultant force on M2 is accelerating downwards, M2G minus T. From Newton's second law, that is equal to mass M2 magnitude of its acceleration. Add these two equations. If you add these two equations, we get M2G minus Fk equal to M1 plus M2 into A. So, but magnitude of kinetic friction is equal to coefficient of kinetic friction to magnitude of normal reaction on M1, that is equal to M1G. So substitute these values, this value of Fk here and simplify it yourself. You get magnitude of acceleration of the masses of M2 minus nu k into M1 whole multiplied by G divided by M1 plus M2. Come on, copy down the solution of this problem. Substitute all the numerical values and simplify it yourself.